Hello, and welcome back to the second episode in the Robotics Programming with Robot Benchmark. In this video, I'll be having a look at the Obstacle Avoidance Challenge and introducing the robotics concepts that it covers there. So before we get too far into the specific challenge, what I'd like to quickly mention is the difference between different types of architectures for programming robots. And two that you most commonly come across are something called a reactive architecture and a deliberative architecture. Now, I don't want to go into a huge amount of detail about exactly what those are, but to say that a deliberative architecture will sense the current configuration of the environment, it'll make a plan based on that sensing that it's done of the environment, and then it'll perform the actions based on that plan. Whilst it's doing the action, it's worthwhile mentioning that it doesn't tend to be doing any updating of that sensing, but it might be that that plan is really short, and so actually it goes back and resenses the environment very quickly. But if there is something that changes during that action, then it possibly won't detect it until it starts the next sensing round. The other approach is reactive, and in this case, there's no planning whatsoever. There's a direct connection between what the robot is sensing and the actions that it's performing. And this is really useful if we're operating in a dynamic and unconstrained environment where actually we don't know very much about the environment at all in advance, but we do need to be able to react to it and navigate or move around or perform some actions in it without, whilst actively taking in that sensor readings. Now, of course, there is a hybrid option which actually integrates the active sensing and reacting alongside the planning and acting. So there is a hybrid model that is most often applied, but actually in this case, we'll be using an entirely reactive approach to programming the robot. So what is it that we're trying to react to? Well, in this particular challenge on Robot Benchmark, they have a child's play area where there's a set of toys that are dynamically dropped into the environment at the start when you first run the simulation, creating a completely different environment each time you run it. And so we can't do any preemptive mapping of the environment. We can't know an exact route across the environment, but we do need to try and navigate safely from one side of the room to the other. So therefore, we need to be able to react using our sensors to be able to cross the room. And because we can't do any planning, then there's no need to actually try and do that planning. Now, in this particular challenge, they do provide you with some starting programs, of course, and in this case, the program that they provide you with is very much based on something called a Braitenberg vehicle. So let's have a look at what this actually is. So Braitenberg proposed a set of very, very simplistic reactive robots that would be able to take sensor input and directly feed those sensor values to the motor values, to the velocities that are used to control the wheels. And so, for example, he had a temperature sensor, which could be used to drive a robot forward or backwards, depending on the temperature it was sensing. And he also had some light sensors that could be directed to, so a pair of light sensors on the front of the robot that could be connected to two separate wheels for controlling the wheels independently. Remember that we mentioned the differential drive configuration last time, whereby the two wheels, you send a separate velocity to each wheel to be able to steer the robot around. And then one of the things that Braitenberg did was to actually have different configurations of the wiring for the robot, such that the robot would display different behaviors based on how the sensors were directly connected to the motors. And in the first case, the 2A configuration that we see on the left here in this diagram, the sensors are directly connected to the wheel on the same side as the wheel that's on the same side as the sensor. And in this case, these are light sensors at the front. When it approaches the light, it will actually increase the velocity of the wheel that is sensing the most light, and that has the effect of actually steering it away from the light. An alternative configuration is to cross over the wires, so the sensor is actually controlling the opposing wheel. And so this time, instead of steering away from the light, the sensor opposite will actually increase the velocity of the wheel, which will actually steer it back towards the light. Now, these are two very, very simple configurations of controlling robots that really don't require a huge amount of electronics or programming ability to actually implement. But when people are observing these very, very simplistic controllers, they often do something called anthropomorphizing the behaviors that they're seeing. They're almost putting human-like interpretations onto those behaviors, trying to interpret what they believe the robot is actually thinking. And so quite often, these two very simple controllers are potentially considered as a fear controller, where it's turning away from the stimulus as it gets closer to it, or an aggressive controller, in where it's actually steering constantly, driving faster and faster towards the stimulus, which is triggering the sensors. So with very, very simple controllers, we can actually create robots that produce some quite interesting behaviors, and behaviors that we can almost interpret in quite a biological and thoughtful way. So let's get back to the actual challenge here. As I say, it's an obstacle avoidance challenge, and the particular robot model that they're using for this one is the Thymio robot. It's quite a small robot, it's smaller than a robot vacuum cleaner, but a nice fun one that's often used for getting people interested in programming robots. It's got 7 infrared sensors on it. So an infrared sensor, it sends out a light signal in the infrared spectrum and then listens or watches for that signal coming back in order to be able to measure how far away the obstacle actually is. And it has 7 of these in total, 5 positioned around the front bumper in an arc, and 2 at the back on a flat panel at the back of the robot. So we can see 4 out of the 5 on this image of the robot here, and then at the back there would be a further 2 infrared sensors. There's also a compass inside, and quite often when we're dealing with electronics, then actually we have 3-axis compass that are able to give us the orientation in multiple different directions for the robot. So if it's on a tilt, or particularly perhaps more useful if we're thinking about quadcopters and helicopters and anything that can fly, or boats on the water. But quite often we do have that same compass inside our mobile robot. But actually all we're interested in is the one axis, which will tell us which direction the robot is actually facing. It's worth mentioning quickly that the range of the infrared sensors is actually quite short. They are a short range sensor typically, unless you get a particularly high-powered infrared sensor. But the sensors here typically have a range of about 10 centimeters. So you can see about its own size in front of the robot. As I say, the target that the challenge sets here is actually to cross the other side of the room, reach the other side of the room with a maximum time limit of 1 minute and 20. And the type of controller it's using here is a velocity control. So I'm going to quickly switch over to the simulation that they provide. So this is the start of the simulation. We've already got some toys on the floor here, and you might just about be able to make out there's a red line on the far side of the room, and that's a target line that we need to cross in order to complete the challenge. Now, when I start the simulation, so when I press play down here, it drops some additional blocks onto the floor in front of the robot, and we now see the robot is driving forward. It has some basic Braitenberg controller in there already, so it will do a certain amount of obstacle avoidance to be able to drive around. It's actually getting slightly further than it normally does on the default program. Normally it crashes quite quickly. But it is getting slightly further. But one thing you will notice, hopefully, quite quickly, is it's not doing anything at the moment to orientate itself towards the red target line. So one thing we do need to make use of when we're solving this is actually trying to add the compass in to improve the performance of getting the robot across the line. I should say each time you run the simulation, it is different configuration of the boxes and where they land. So I think that's possibly the only time I've ever seen it complete with the default program. But I suggest is when you want to reset the program, you first of all pause it, you press the button on the left to reset it back to the start, and then you can press play again when you're ready to actually watch it go. But before we do go any further, then let's actually have a look at the initial program that it provides. So just to remind you, I've right-clicked on the robot itself and clicked on the edit controller, and that brings up the initial program for me to be able to start editing this. So like with last time, we import the robot from WebOps so we can actually start to interact with it. In this case, we need a timer as well to be able to keep track of the simulation time. There's a couple of constants that are defined specifically for using this robot. So the maximum velocity at which the wheels can turn, and a distance calibration for the ultrasonic sensors. We then gain access to the left and right motors. And importantly, we also gain access to the front set of infrared sensors. So each of these variables is directed to point at one of those front sensors, and we can see the outer left, central sensor, central right, and outer right. So the 5 going around the front. Each of those sensors then needs to be enabled, so we need to turn on the sensor so we're actually getting readings from it. And then I mentioned that it's using the velocity control for this one. Now, this particular robot language is slightly odd in the way that we switch from position to velocity control. And by default, it is in position control. And this is where you're defining a set point that you want that particular joint to turn to in order to be able to move that joint. Now, in this case, we really don't want to be able to be setting positions for that. We want the robot to just be able to drive across, and we don't know how far it's going to actually be driving. So we need to turn off the position control. And the way this is actually done here is by setting the position value to infinite. So this float in Python will give us an infinite number. And by using that to set the position for each of the motors, we can essentially say we're not worried about position control. And then that will switch it over to velocity mode, so we can then specify what velocity we want the wheels to turn at. Now, they defined a maximum velocity up at the top, but it's quite likely that you don't necessarily want to be driving at that maximum velocity all of the time. So they do set this initial velocity as a proportion of that maximum velocity and use that to start the robot actually driving along. So they set the same initial velocity to both left and right of the wheel so it drives in a straight line forward. We then have this while loop, which is what's actually going to be acting, and where most of our implementation will go. We will need to add some initialization for the compass up ahead, but most of it will go inside this while loop. So the first part of the while loop is actually reading from those infrared sensors. So from the sensors, we're getting the value, and that's a proportion of the distance sensor calibration constant that was defined up at the top for us. So you don't need to do a huge amount you don't want to be modifying that bit too much, but you do potentially then want to be making use of these values from the different sensors. You might find it useful or informative at various points to print out some details, and I'll show you how to do that in just a moment, how to see those values whilst it's running. But just to quickly finish off, this 2 lines at the bottom is the actual Braitenberg vehicle implementation. And this is where we're essentially taking a couple of readings from these infrared sensors and directly using those to set the velocities that we're sending to the wheels. So in this case, for the left wheel, we're looking at the central right sensor value and the outer right sensor value, so the 2 right-hand infrared sensors. We're taking the average of those 2 sensor readings and then subtracting that from the initial velocity. Similarly, for the right-hand motor, we're taking the left-hand sensor readings and the averages of those. And in this case, we were also considering the central sensor value. Whether that should be on both or just on one is I'll leave for you to decide. But this is somewhere where we can actually start to expand on the controller to be able to improve the performance of the robot driving across the room. And that, of course, is used to adjust the initial velocity. So let's have a look at printing out some values from here. So in Python, we can use the print command, and we can then specify I want to print out the outer left sensor value, and let's go for the outer right. So I'll only print out the 2 here, just so we can see what's going on initially. So if I run that now, didn't actually save the program before I ran that. So let's just reset that. So remember, if there's still a start there, then you save the program before running it. So I've run the program. Whilst the program is running, you can get certain information or the console log by clicking on this console button down here. So here you can actually see that as it's going along through that loop, and as I say, it's got stuck here with the default controller, we're now actually seeing what those sensor readings are that are coming from the robot. I'm quite impressed it hasn't actually totally failed and hit anything there, but I'm pretty sure it should have done. But you can see that you can get the readings from those. So one of the sensors that the robot has is, of course, this compass, but at the moment the compass isn't included in the code. If we do look at the instructions up here, it does give you some information there as well about how to access the compass. But we can have a go at actually adding this to our programs quickly ourselves. So if I reload the controller, bring that back up again, the first thing we need to do up at the top is to actually import the compass, sorry. And once the robot is actually initialized, like we get with the infrared sensors, we then also want to get the compass reading. So we can get compass sensor. I apologize, I cannot type and talk at the same time without making a lot more mistakes. So there we go, we've got access, so we've got a variable that will reference the sensor for us. And again, like we had with the infrared sensors, we then also need to enable the compass sensor. So I'm just going to add a comment here, enable compass sensor. And with that done, we can now actually start to getting the readings from that compass at each time step. So inside this while loop, like we're getting the readings from the infrared sensors, we now also want to get the reading from the compass. And we can do that with compass, create a variable called compass values. Now at this stage, it's important to remember that the compass is a 3-axis compass. It's not like your magnetic compass where it only gives you a single value pointing towards north. It is a 3-axis compass. So if we were actually to print the compass here, I'm just adding a label in there so I know what it is I've just printed, and save that. And hopefully now if I resume this, let's just restart it. Can't type. Got a typo in my program on the very first line that I added. I should have spotted that one. So I can't type and talk at the same time. So there we go, we're now getting compass readings. And we can see how they change as the robot changes direction to give you some indication of what these values look like. And I'm just going to pause that there a moment. And what we have is the 3 different axes that can be produced here. Now, these are essentially in Python, they're in an array or a list, more accurately for Python, of length 3. And so the x-axis is the first index in that array. So if we actually want the x-axis, then capital A, we need to obtain the compass reading from the first index in that array. Remembering, of course, that in computer science and arrays, when we're programming, arrays numbering starts at 0. So referring to index 0 from that compass values array will now give us the x-axis, which is the one that's actually important for telling us which direction we want to be pointing in. And that wants to be as close to 0 as you can get it. Now, interestingly, from a Braitenberg perspective, what you can do with that x-axis is you can adjust the initial velocity, adding the x-axis value to the left motor and subtracting it from the right motor, and that will orient gradually the robot back towards the target direction that we want to be heading in. But of course, how you integrate that is a part of the challenge. So in terms of actually tackling this challenge, then I would say there's 2 main priorities that you need to address first. And that's to actually make sure you're able to avoid the obstacles. And it's quite likely that you may well find some scenarios where actually you end up pinned in a block in an area where you actually have to turn all the way around in order to get back out of it, and your controller may or may not be able to deal with that. But other runs of the simulation, you're able to get through no problems. I would say try and make sure you're able to get through most of the time, and if there's the odd scenario, you can choose to develop your controller further to deal with those special cases, or you can be satisfied that your robot is able to deal with it most of the time. And so one possible approach for doing that is actually, quite simply, you slow down when you're near the obstacles. So the closer you get to obstacles, then the slower you potentially want to go. And that will increase your ability to steer and navigate around the obstacles without actually crashing into them, rather than just driving straight forward into those obstacles. The second key challenge to actually try and make sure you're finishing the challenge is, of course, heading to the finishing line. If the robot's going off at an angle, then you may eventually cross the finishing line, but it's definitely not going to be a particularly quick time. So you do want to be making use of the compass in order to be able to steer the robot back towards that finish line when it's been knocked off target by the obstacles. So some things that you can have a look at is currently there's 5 sensors around the front of the robot that are equally being considered when it comes to how much to turn the robot. If things are at the edges of the robot, you might not actually want those to have as much influence to how much the robot turns as the ones that are directly in front of the robot. So you could potentially consider that. You may want to adjust the speed of the robot, speeding up and slowing down, depending on what obstacles are around you. And of course, incorporating the compass to be able to steer back towards the target point. If that is all successful, then hopefully what you might end up with, and if I just actually quit this simulation and go back to here's one I programmed earlier, with any luck, we'll have a slightly more successful, hopefully quite quick simulation crossing the room. So not as quick and efficient as I might have hoped, but it did certainly navigate safely between all of the obstacles and reached the far side of the room, which is of course what we're after here with our programs. So I'll leave it there and good luck for the challenge. And in the next video, I'll be looking at the square path challenge on Robot Benchmark. Thanks very much and see you next time.